Satellite designs for defense and deep space applications require a source of electric power that is more reliable, efficient, and survivable than existing power sources. To address this need, the Dynamic Isotope Power System, or DIPS, is being developed. DIPS is a nuclear-based power generation system for the 1 to 10 plus kilowatt range. It employs a general-purpose radioisotope heat source utilizing plutonium oxide and converts thermal energy to electric power using a dynamic engine such as an organic Rankine cycle or ORC. Sunstrand's proven ORC offers advantages over other dynamic systems that result in low technical and financial risk and lower life cycle costs. These advantages include a low operating temperature, the use of conventional rotating hardware, a proven working fluid, a small physical size, and a mature, reliable technology. DIPS comprises 4 main sub-assemblies: a vaporizer, a power conversion unit, a condenser, and a radiator. The vaporizer utilizes a general-purpose heat source developed by the Department of Energy to vaporize the working fluid and transfer heat via a tube-type heat exchanger that is bonded to the shell of the vaporizer. The heat addition in the vaporizer is equivalent to single-phase sensible heating. Vaporization of the working fluid occurs at a pressure greater than its critical pressure. Therefore, no elongated isothermal boiling zone exists, as in a subcritical cycle. The vapor exits the vaporizer in a superheated state. The DIPS power conversion unit includes a combined rotating unit, a regenerator, and a fluid management device. The combined rotating unit consists of a single-stage turbine, alternator, and pump. The turbine converts heat energy to shaft power to drive the alternator and the system feed pump. The regenerator extracts superheat from the turbine exhaust to preheat the working fluid prior to entering the vaporizer. And the fluid management device performs the phase separation function normally provided by gravity in terrestrial applications. The working fluid is condensed in a shear flow-controlled condenser. Heat, not converted to electricity, is rejected to space by a heat pipe radiator that is coupled to the condenser. DIPS offers several advantages, including high survivability, achieved through the use of a heat pipe radiator. This heat pipe design provides hardening advantages against such threats as lasers and particles such as micrometeoroids. And DIPS' low temperature operation minimizes its infrared signature. DIPS allows spacecraft to be very agile and maneuverable and is capable of handling high acceleration in excess of 5 Gs. The orbital insensitivity of DIPS' isotope heat source allows operation in the Van Allen belt and precludes the necessity for ecliptic energy storage. Spacecraft pointing requirements are also reduced, and minimal radiation from the isotope source requires shielding for only the most sensitive electronics. Sunstrand's quarter-century of space power-related experience includes the design and manufacture of 12 different ORC systems that have accumulated over 118,000 hours of operation. This experience is highlighted by the Advanced Solar Turboelectric Concept, a 15 kilowatt liquid metal rubidium Rankine cycle designed for space power application. The 100 kilowatt total energy system designed to provide electric power and heat energy for terrestrial applications using toluene as its working fluid. A 1 kilowatt remote communication unit designed for unattended, reliable operation using a supercritical toluene cycle. The 600 kilowatt waste heat recovery system that is a toluene ORC designed to recover energy from industrial waste heat streams. The unit shown operates at Continental Whitecap in Hayward, California and has accumulated over 18,000 hours. The DIPS ground demonstration unit. This 1.3 kilowatt flight prototypic unit accumulated over 10,000 hours of vacuum chamber testing, demonstrating high reliability and efficiency in a simulated space environment. In 1978, following a comprehensive ground demonstration program, the Sunstrand ORC DIPS system was selected over a competing Brayton cycle DIPS unit. And the Space Station Solar Dynamic ORC, a 25 kilowatt unit being developed for the space station's initial orbiting capability. This toluene-based ORC unit is similar to the DIPS design, but uses a solar receiver in place of DIPS isotope heat source. Future expansion may result in an 8-channel solar dynamic ORC system responsible for supplying the station's total electric power needs. Sunstrand's space experience with rotating equipment includes the Space Shuttle turbine-driven auxiliary power units, coolant pumps, and fans. Sunstrand has been expanding the ORC technology base to provide a reliable power-generating system for space applications. Emphasis is being placed on the working fluid stability and its management. Use of an organic working fluid, such as toluene, in the Rankine cycle eliminates concerns of liquid formation during the turbine expansion process and yields higher thermodynamic performance. Toluene's thermal stability was demonstrated in 1971 by Sunstrand's isothermal capsule tests and verified in 1985 by Argonne National Laboratory. The fluids database is being expanded through dynamic loop testing at Argonne, up to 600 degrees Fahrenheit, and at Sunstrand as part of NASA Lewis Research Center's Advanced Development Contract, up to 850 degrees Fahrenheit. This toluene stability loop, which began operation in June of 1986, provides accurate time at temperature simulations of the DIPS Rankine cycle, demonstrating toluene's 30-year fluid life under flight prototypic operating conditions. The two-phase ORC working fluid is managed in the zero-gravity space environment by controlling the vapor-liquid interfaces. A rotary fluid management device, or RFMD, creates an artificial gravity of up to 200 Gs through the centrifugal force generated by its rotation. This device thus provides a control point so that saturated liquid can be supplied to the system feed pump. It also provides a convenient location at the cold end to sense and remove non-condensable gases. Additionally, the turbine's momentum can be canceled by appropriate sizing and location of the RFMD on the turbine's axis. Therefore, the DIPS will have minimal impact on the spacecraft's attitude, an important characteristic for missions with precise pointing and tracking requirements. The RFMD has completed all attitude ground testing and is scheduled for a flight test in NASA's KC-135 zero-gravity flight test facility in August 1986. Condensation of the working fluid is accomplished by using a shear flow-controlled condenser. This vapor-liquid interface is controlled by maintaining high fluid velocities in tapered channels and ensuring that the vapor is completely condensed prior to exiting the condenser. The hybrid DIPS configuration offers several attractive integration features that can further improve the DIPS efficiency and reliability. This configuration employs dual independent operating channels that share a heat source and a radiator, and it incorporates thermoelectric topping that provides DC power independent of the Rankine cycle. The hybrid DIPS provides high survivability, enhanced by using advanced heat pipe technology for a hardened radiator. The spacecraft can be configured with either a cylindrical or a planar radiator, thus providing the flexibility required for various spacecraft needs. Use of proven organic Rankine cycle and thermal electric technologies translate to high system efficiency and reliability. Redundant dynamic hardware provides operational flexibility in achieving high power system reliability. Finally, each of these features is achievable while maintaining a compact size and low weight. The net result is increased flexibility of integration and a high system efficiency. Sunstrand has met today's space power requirements with the dynamic Isotope Power System. The inherent reliability and efficiency of the organic Rankine cycle, plus the flexibility of spacecraft integration, makes DIPS the space power system of the future.